Hi there! Have you ever wondered why some study tricks seem to work miracles while others fall flat? Scientists have been testing memory for ages to figure that out. Today, we'll explore classic experiments that shaped our understanding of how our minds store and recall info, and we'll go deeper into how memory systems actually work. Ready? Let's begin. Memory research isn't just for labs or dusty books. It changes our everyday lives. The studies we're about to see connect to theories you might have heard of, like the multi-store model or working memory model. They show us how short-term memory, long-term memory, and other cognitive systems cooperate or clash. Let's think about how we handle info. We have sensory memory, a brief holding zone for things we see or hear, lasting only seconds. Short-term memory, or working memory. We keep info here for a short time, maybe a few seconds unless we rehearse it. Long-term memory, where knowledge or experiences can stay for years. Experiments help us see if these ideas hold up. They reveal how we can improve learning, manage big tasks, or help people with memory issues. Have you ever done a memory test in school or just for fun? How did it go? Share in the comments. Imagine two groups. Both see the same list of 15 random words. Group A repeats them quietly for 2 minutes. Group B does a distracting task, maybe counting backwards. We predict Group A recalls more because they rehearsed. Group B was too busy to loop those words in their head. This lines up with the multi-store model. We move information from short-term memory to long-term memory by rehearsal. If we don't rehearse, information slips away. Repetition can really boost memory. That's why spaced repetition apps or reading notes aloud can help. It's no accident that teachers say, review your notes often. This experiment shows even a little rehearsal can mean a big difference. In real life, memory is more fluid. The multi-store model is simple but still useful for showing why repeated practice helps move data along. Now let's look at working memory. One group does tasks one by one, like repeating numbers backward or sketching a visual pattern. Another group tries to do both tasks at once. People doing both at once usually do worse. Why? Because working memory has multiple parts, like a verbal loop for language and a visuospatial area for images. Each part has limits. When tasks overlap, they fight for space. This lines up with Baddeley and Hitch's working memory model. We have phonological loop for sounds and speech, visuospatial sketchpad for pictures and space, central executive, the boss that decides who does what. If we overload the same system, like two verbal tasks, mistakes go up. Ever try a podcast while reading a tough text? Hard, right? That's your memory system getting overloaded. This also explains how some people can easily listen to music with no lyrics while studying, but have trouble if the music has words. They're tapping into the same verbal resources in the brain. Our third classic study is about levels of processing. Participants see words and do different tasks. Shallow, is it uppercase or lowercase? Intermediate, does it rhyme with something? Deep, does it fit in a sentence like, my cat loves to chase a blank? When tested later, words processed deeply, thinking about meaning, stick better than those processed shallowly, like just looking at caps. This reveals that deep processing forms stronger memory traces. If you only skim words, you'll forget. But if you connect them to personal stories or real-life examples, you lock it in more securely. Try focusing on why something is true, or how it relates to what you already know. That deeper approach goes a long way. This concept ties back to semantic memory, facts and ideas we hold in long-term storage. When we process at a semantic level, we're linking new info to existing knowledge, making retrieval easier later. These experiments each highlight a different piece of the memory puzzle rehearsal for multi-store transfer. Dual task performance for working memory, depth of processing linking to long-term storage. But let's not forget about other memory systems. Sensory memory, brief, fleeting, like a quick snapshot. Short-term memory, our mental workspace, also known as working memory. Long-term memory, includes episodic, personal experiences, semantic, facts, and procedural, skills. Understanding these helps us see why each experiment works the way it does, from seeing a small capacity for STM to the difference deep thought makes in forming strong LTM traces. Memory experiments also show how cognitive control matters. Our central executive decides what to focus on, like ignoring distractions or switching tasks. If it's overwhelmed, performance drops. Brain areas help out too. The prefrontal cortex is big for controlling focus. The hippocampus helps form new long-term memories. The parietal cortex can handle spatial tasks. When we do a dual task test, these regions coordinate or compete, depending on if tasks clash or mesh. We also know from research that deeply emotional or distinctive info can stand out in memory. That might not show up in these classic lab tasks, like a list of random words, but in real life, emotional events form flashbulb memories that we recall vividly. So how do these experiments help us in daily life? Studying. If you want to remember new vocab, rehearse out loud, like in the multi-store model. Multitasking. Trying to listen to a lecture and text a friend at the same time might hamper both tasks. We see from the dual task study that working memory can be overloaded. Deep learning. If you want to truly grasp a concept, connect it to existing knowledge, like in the depth of processing experiment. In education. Teachers might arrange lessons so that students actively engage. No more just copying notes. They might also limit how many tasks you juggle at once. In the workplace. Understanding working memory helps in planning tasks, reducing overload, and training staff. If a job demands quick shifts between visual and verbal tasks, we now know that can strain memory. Memory disorders. People with certain issues, like ADHD or certain forms of amnesia, may show weaknesses in these areas. The experiments and models guide therapists or doctors in designing strategies for them. Scientists keep refining these classic experiments. They look at brain scans to see which parts light up during rehearsal or dual tasks. They test how emotional or negative info changes memory. They ask how new knowledge about neural connections or memory consolidation might adjust these old findings. As we learn more, we can update theories, like adding the episodic buffer to the working memory model, or exploring deeper ways to describe how we store personal events versus facts. Memory science is alive and growing. Even these classic experiments adapt to new methods, new brain imaging, and new questions. We've seen 3 core experiments that link up with major memory ideas. Rehearsal and multi-store repeating info helps it reach long-term memory, dual task and working memory. Trying to handle 2 tasks that tap the same resource can cause overload. Depth of processing. Thinking about meaning cements info more deeply. These lab studies shape how we study, teach, multitask, and handle life. They remind us that memory isn't just put it in, get it out. It's a living system, with layers, cues, and emotional factors all mixing in. Thanks for watching. If you enjoyed this, please like and subscribe, and let me know in the comments which experiment surprised you the most. See you next time, when we tie all these models and findings into an even bigger picture of how we remember.